Good morning. Can you let me know if you hear me, please? Hello.
We can hear you.
Thank you, Savannah. All right, it's 9:30. We'll get started. First of all, I wanted to alert you to the fact that while there was homework that was actually part of tests for tests 1 and 2, that's not the case for test 3. The situation is, if we look in the test 3 folder, there is a practice test, but same situation as we had before, but this practice test, test 3 will be worth 100% of your test grade. The way it was with test 1 and 2 was that 20% was homework, but this is not the case here. And there are other quizzes. And you'll find them in these individual folders along with resources for those individual topics as well. So there's a lot of stuff in here in these tables, as well as these quizzes. And these quizzes are all extra credit. Now, the way this works out is that everything you get on these credit quizzes that are in these folders gets divided by 2 and gets added to your score as extra credit. Overall, it's worth about 7 points, I think. We can check that in the grades, but you can follow your progress by looking at the grade section under test 3 complete, and as you complete these extra credit quizzes, you'll see your grading improve as you get them. You don't have to get 100% on the quizzes to get the points. You get whatever you get. The idea is that it's kind of similar to test 1 and 2 in that you have to do a practice quiz first. That will alert you to the kind of formatting that's expected, and then you get 80% on that, and it opens the credit quiz, and then you'll get 2 attempts on those, and they're all extra credit. Some of them do deal with material that's not on the test. I'll say that some of them do deal with material that's not on the test, but it's all extra credit. All of it, the whole thing's extra credit. But they're worthwhile. They certainly give you a good guide as to whether or not you're understanding the material. Now, the other thing I can tell you is that for test 3, there are these videos, and these videos will tell you exactly how to do the problems. Now, they don't give a whole lot of background, and it's not going to be sufficient to not do anything and then just look at these videos. But if you're not sure about how to format something, or you're not sure what I'm looking for, then watching these videos can be helpful. And you'll see there's one video for each question that's on the practice test. And remember, the real test, the test 3, is just an exact copy of the practice test. just like it was with tests 1 and 2. Does anybody have any questions about the way things are going to be for test 3?
So those extra credit quizzes, I have to get the 80% on it, and then it unlocks the extra credit for it, correct?
That's right, the practice quiz. But you can do the practice quiz as often as you like.
Okay.
And it's really the same quiz. So, I mean, if you don't want to waste your time wondering about the formatting, just open the practice quiz and hit submit and look at the answers.
Yeah.
Right? I mean, if you don't want to say, oh, look, I don't want to have to guess what he wants for the formatting, I'm just going to look at that. And that's fine. I don't mind that. The whole point of having the practice quiz there is so you know what the formatting is going to be like for the credit quiz. I don't want the formatting to be the reason people don't pass the credit quiz. That's the main point.
So basically all the quizzes, they're extra credit so they don't go towards the grade, and then your test is 100% of your grade.
That's right, but the extra credit does get added to your grade. I mean, it becomes part of your grade. But
it's the overall grade, not just the test grade.
I'm sorry.
Like, I didn't mean to interrupt you, but yeah, I was like confused on that. So like, so my understanding right now is like the test is worth 100% of the test 3 grade, right? Then any extra credit is added to the test 3 grade, not the overall grade.
Well, it's added to, that is the overall grade. So it's added to the test 3 grade. So if you got 5 out of the possible 6.5 points or 7 points or whatever the extra credit is worth, then that 5 points gets added to your test grade.
Gotcha. All right. Yeah, that makes more sense. Thank you for clearing that.
Now, the extra credit closes 11:59 p.m. on the night before the test 3 is due. Test 3 is open now. You could take it whenever you like, up until the day that it's due. I want everybody to be clear on that. Does anybody have any questions? Okay. Now, I've had some issues with the PowerPoints not opening properly on this computer, so I'm going to be using the printed versions. It's the same thing, it's just going to be printed. The formatting of these doesn't change, so that's okay. All right, so we're going to be dealing first of all with energy and energy changes. So if we look at today, we look at the syllabus here, we can get an idea of what we're going to be covering. I sent you all an email. I let you know about October 26th. There won't be a Zoom session that day. I'll work around it. We'll still get to cover everything, I think. But you still, there's nothing to stop you from watching the videos that are in here. The videos that tell you exactly what we would be doing that day anyway. And, the topics we're covering that day aren't incredibly difficult, I don't think. All right, but for today, as you can see, we're doing heat and work, enthalpy, and estimating delta H by bond energies. All right, so let's look at energy and energy changes. This is actually an animation. It has these little molecules moving around, and that's a form of kinetic energy when you've got these molecules moving around, and energy is what causes them to move around. We've got our 2 types of energy. We've got kinetic energy and we've got potential energy. Kinetic energy is energy that results from motion. And then we've got potential energy, which is stored energy essentially. So let's say you got this example of this guy on a bike riding up a hill. At the top of the hill, he has potential energy.
Hello, Moto.
Let me turn that down. Sorry about that. It's incredibly rude, wasn't it? All right. So we're with potential energy. You've got this guy at the top of the hill, or a girl, I suppose, and then goes down, and that's kinetic energy. Once that potential energy gets used up, we've also got chemical energy, and we're going to be focusing a lot on that. That's energy stored in bonds. And there's, this would be an example, this is ethane and oxygen. So this would be combustion of ethane, which is a very, very combustible gas. And then it will form CO2 and water and heat as well. And that heat is as a result of the energy tied up in the bonds here. We'll talk much more about that soon. Now, whenever we're talking about transfer of energy, it's always from the point of view of the system. So the system is what is either going to be releasing energy or absorbing energy. So if the system releases energy, then the change in energy becomes negative. In other words, it's losing energy, but it's always from the point of view of the system. The system is losing energy, so the energy goes down. And in the other situation where energy is being absorbed by the system, then energy goes up. I think that should make sense to you, but it only makes sense if you think of the system, that's what we're actually talking about, the situation we're actually talking about, as being the focal point. Everything is from the view of the system, how it looks from inside the system. Now, when we talk about the surroundings is just the universe. It's everything that's not the system. And of course, energy cannot be created or destroyed. So we talk about exothermic, that's heat going out. Exo meaning out, like external, the word external. Thermo meaning heat, so heat out. Heat absorbed is endothermic. So endo means inside or going inside. So when we talk about thermochemistry, we're talking about the heat that's transferred during chemical processes. So let's say we've got a match and we light that match. The match is going to be the system. And what happens is that during that chemical process, energy gets released. And that's why the energy is now lower in the situation of the match that's burned up. But energy has been released to the surroundings. Now, when we're talking about chemical reactions, there's two situations that really contribute to the amount of energy in the system. And I think a lot of this can be explained by looking at a piston. So a piston will allow us to do work on a system. And what we can say is that the change in energy of a system that's in a piston here is going to be the result of two things. Delta E, which is the internal energy, is going to be Q plus W. Now, Q is the heat released or absorbed by the system. So this could be a chemical process that's releasing or absorbing heat. And W is work done on or by the system. And what we're talking about here is the effect it has on, say, a piston. So let's say we've got that situation where heat is being released or absorbed. Then we can see that, like I had said earlier, if heat is released by the system, then Q is going to be negative because it's losing heat. If heat is gained by the system, then Q is going to be positive. It's greater than zero because heat is being gained. If work is being done by the system, that is like it's pushing up on a piston, for example, that means that work is negative. Think of the reaction as losing work if it's actually doing work on a piston. Now, if the piston is being pushed down by some sort of external force, then work is being done on the system, and that will contribute to the system's energy. So work will be greater than zero. So if you think of it in those terms, then it's not too bad. Does anybody have any questions so far?
I kind of had a question, but I'm not sure if it will relate to later. It was more or less along the difference between like, what was it? Chemical energy versus like kinetic energy and potential energy. So would chemical energy be like, so when it involves with kinetic energy, that there's some heat involved with that, right?
Well, kinetic energy, not necessarily. I
Okay.
mean, kinetic energy is energy that's due to motion, specifically motion. Now, sometimes that motion is due to heat. Sometimes it's due to something else that's going on.
Okay. And then as far as like chemical energy goes, like you could go to say that like with like those hydrogen cells, like I know they're coming up with a hydrogen generator that like when
Right.
hydrogen bonds with oxygen, the electron travels through the wire and then they use that for energy. Would that be considered a form of chemical energy?
Yeah, that's chemical energy because in the end, it's about the difference in energy between reactants and products.
Okay.
And we'll see that when we look at some examples.
Thank you for clearing that up.
All right. So this is just a summary of what I had just said here. When heat's released from a system, Q is negative, it's losing heat. Heat absorbed, Q is positive, it's gaining heat. Work is done by the system. It's kind of like losing work, W is negative. And when work is done on the system, W is positive. So let's look at some examples of these kinds of questions. You'll get one of these on the test as well. It's not a very difficult question if you are aware of what I had just stated here. All right, calculate the overall change in internal energy for a system that absorbs, and look at that, the key word is absorbs there, 326 joules of heat, that's Q, and does 200 joules of work on its surroundings. So it's losing 200 joules. So when you look at the calculation here, you can see that it's going to be Q is, because the keyword is of absorbing heat, Q is going to be positive. It's doing work on its surroundings, so W is negative. If it's doing work on its surroundings, it means it's losing work. So W is negative. So that's how I want you to think about it. So then we just apply delta E is Q plus W, apply the correct signs to Q and W, and then we come up with our answer. As far as significant figures go, this is an addition-subtraction situation. So it's going to be based on the number of places past the decimal point. Does anybody have any questions so far?
So eternal energy is just energy stored, right?
Well, it's in the system. It's the energy the system has. Yeah.
Oh, so it's the energy trapped within the system.
Yes, you can look at it. Yes.
Okay, so it can't escape. So like say we have so much potential, we have so much energy on this planet and we're constantly getting more energy from the sun. But if the sun stopped giving us energy, then it would be the eternal energy of the planet would have that set amount of energy and then it can't.
Well, but it could lose that energy to the surroundings, right?
That's true. But like, I guess if you put it into like, if you took like a sun, you just trapped all the energy inside of it. That's the eternal energy
Right.
of the
Then
sphere.
yes, that would be internal energy. Yeah.
Oh, like one of those self ecosystems. I don't know if you're.
You mean like those biodome type situations?
Oh, but yeah, but I guess you get energy from the outside.
Yeah. So yeah, so you got to remember that this delta E business here is also due to energy that's coming in and work being done on the surroundings. But overall, that none energy doesn't get created nor destroyed.
Gotcha.
Okay, so the next one here, calculate the change in internal energy for a system that releases, and the keyword there is releases, 2.73 kilojoules of heat, that's Q, and 7.34 kilojoules of work is done on the system. See, the keyword there is on the system. And that means that in this case, work is done on the system, so W is positive, and it's releasing heat, so Q is negative. So again, we just apply the correct signs and then just do the addition. Again, two places past the decimal. All right, does anybody have any questions about the delta E equals Q plus W kind of problems? Okay. So a lot of the reactions we do are at constant pressure, at atmospheric pressure. And that affects, I'm not going to go into it too much, but we can talk about work as being the result of pressure times volume, the change in volume here. And we can also, again, once we have no change in volume, then that will allow us to equate delta E, the internal energy, to the amount of heat that we're getting from the reaction that are being absorbed or released. So we've got constant volume, usually got constant pressure as well for a lot of these reactions. And we end up with this system, this thing called delta H, which is called enthalpy, which ends up being the energy simply released or absorbed by the reaction. And this gets drawn back to the energy that's present in the bonds in the reactants and products. So I don't really want to go into this too much about how we get the delta E at constant volume and how that relates to enthalpy. Really what I want to focus on is the fact that once we assume that we're doing a reaction at, say, constant volume here or constant pressure, then we can have our enthalpy of reaction, delta H, as being simply the heat released or gained by the system. And that's all I really want you to get from this presently. So when we look at, say, heats of reaction, delta H, and this is just due to the fact that we're doing the reaction at constant pressure or constant volume, then we are now focusing on simply what the energy of the reactants is versus the energy of the products. Now, I'm not going to go too far into these kinds of energy profiles. Really what I want you to focus on is the fact that we have the energy of the reactants up here. The reaction coordinate is the reaction going from the reactants to the products. There's going to be a certain amount of energy required to make the reaction happen. That's called the energy of activation or activation energy. And you can imagine it as being like, let's say you are down the bottom of the hill here and you roll the ball up a hill. If you don't put enough energy into the ball, it'll stop, say, right here, but then it will roll back down. That's what happens in chemical reactions as well. You don't put enough energy in the molecules, they won't react. But if you do have enough energy in two molecules for them to react, then they'll react and then they'll form the products. Now, the focus I want you to have here is on the reactants and products and where they are relative to each other. Here, the reactants have a certain amount of energy, and now the products have a certain amount of energy. You'll notice that the products are lower than the reactants. You see that? Reactants and products. I'll stop right here for a second. Does anybody have any questions about what I'm trying to talk about here? Now, when we're talking about this delta H value, that's the energy change. This is the enthalpy that we've been talking about. It's the difference in energy between the reactants and products, and it's always products minus reactants. So you can see that if products is a small number and reactants is a big number, then the value is always going to be negative. The reverse of this is an endothermic process. This is where energy gets absorbed by the system. And you can see that reactants are down here and the products are above. So products minus reactants, you've got a big number minus a small number, that's going to result in a positive value. So all I'm trying to get at here is that when heat is released, delta H is negative. When heat is gained, delta H is positive. And it's all because the products either have less energy or more energy than the reactants. Now, the other thing I'll point out here is if products have less energy, what that means is it's more stable. The products are more stable. And the difference in energy was the energy that was released in order to make that system more stable. And this is why a lot of chemical reactions go in the first place, is because whatever they're producing as products is more stable than what we had in the beginning. And that's certainly true of a situation like this one here, where we've got ethane and oxygen. The products, carbon dioxide and water, are a lot more stable than the reactants we were using to begin with. So those being more stable is what helps the reaction to go in the first place. And then there's a heat released, and that is going to be the difference in energy between the two. Does anybody have any questions?
So heat is energy equivalency, right? Like
in this instance, yes, it's the only thing we're really considering, and we're using it as a guide to tell us how much energy difference there is between the reactants and products. It's the energy that was tied up in the chemical bonds.
So are we using heat as a metric to measure energy?
In its own way, yes. And in this case, heat is the energy that we're talking about. Now,
Okay,
heat and temperature are two different things,
yes.
but heat
I
and
get-
energy in this case are pretty much equivalent.
Okay. Is there other ways to measure energy besides heat?
Well, in chemical processes, not really.
Okay.
But in many other processes, yes, there are other ways to measure energy.
Okay.
But we're just going to be focusing on heat changes here, enthalpy.
Gotcha.
Okay, so what we've got for the reactants is what we call heats. In order to measure the amount of energy tied up in the reactants or the products, then we have this thing called heat of formation. Now, a heat of formation for elements in their natural state is 0. So let's talk about what we mean by elements in their natural state and this heat of formation business. Okay. So this is the important statement that I want you to really appreciate. Heats of formations of elements in their natural state are 0 kilojoules per mole. Let me show you an example here. Let's say we had, well, we'll just make it CO2 gas. Can anybody tell me what elements make up CO2? It's not a trick question.
Carbon and oxygen.
Okay, carbon, right. But carbon in its natural state, well, what's carbon's natural state? Well, it's going to be solid, but specifically graphite. A lot of you have lead pencils, right? Well, that's what lead pencils are made of, graphite. Carbon in solid form. Now, this is its natural state. Now, the heat of formation, the delta H of formation of this is 0. The delta H of formation of carbon, solid graphite is 0. Okay. So oxygen. But what is oxygen in its natural state? Anybody know? Is it just O?
Is it O3?
No, it's not O3. That's ozone. Ozone does exist, but it's not really considered to be oxygen's natural state.
Okay.
Anybody else know?
No. Just O by itself.
No, it's not O by itself either. It's O2, and it's in gaseous form. And the delta H of formation of that is 0. Now, CO2, when these two things get joined together, the carbon and the O2, a certain amount of energy gets released. And the delta H of formation of this compound, CO2, is negative, I think it's 393 kilojoules per mole. Oh, actually, I know I can get, yes, it's 393.5 kilojoules per mole. I can see it from over there. And you might be wondering, where do I get that from? Well, you get that from a table. And I'm going to show you what that table looks like. Hang on. Here we go. Okay, let's see if we can find this table here. So I think it's in the, is it in the heat and work folder? Here we go. Yeah, there it is. So don't worry about the S0 column. That's something we'll deal with when we get to Chem 2. But this gives you a list of all of the heats of formations of these compounds. So you can see the CO2 one we get by looking at carbon. So we can find it here, CO2, there it is, negative 393.5, the unit being kilojoules per mole, as we see up here. And again, that energy is the result of taking carbon in its natural state, which is carbon solid graphite, and O2 gas. Now, if you take a close look at a lot of these heats of formation, you'll see that for aluminum solid, for example, it's 0. For barium solid, it's 0. For beryllium solid, it's 0. So, you know, a lot of people seem to be struggling with trying to figure out what the natural form of O2, of oxygen was. So how could you find that out? Well, all you do is go to oxygen and you look for the one that has 0. That tells you its natural state. So you look at this. You've got O by itself would be 249.2. O3 is 142.7, but O2 gas is 0. So that tells you its natural state. So anything in its natural state has a heat of formation of 0. Why? Because elements are the basic things that are building blocks of all compounds. They're the basis. Everything that they have is 0. So when we go on.
I just made a quick observation. I just wanted to see if I'm right on this. So I see that the negative numbers are usually byproducts of reactions. So like, for example, CO2, it has the potential to store energy more than it has to give off energy. It wants energy.
I would say that because it's negative, it means that a lot of energy was released when it was formed, which means that it's a whole lot more stable than the elements that created it. That's all you can really say.
Okay.
Right? I wouldn't say anything more than that about it. But the more negative this energy is, the more stable it is. I could definitely say that.
Okay.
All right, so how's that apply to what we've been talking about? Well, if we've got a reaction, here we go, right? And we want to find out the delta H naught, or the enthalpy, or the heat released by that total reaction, we can apply this equation here, which I'll write down the bottom here. So delta H naught, the naught means standard conditions, and that's 1 atmosphere, 25 degrees Celsius. But you don't have to be too concerned about this. You can assume that we're dealing with standard conditions pretty much all the time anyway. So that really isn't going to be too much of an issue. So this symbol here is called sigma, and it means sum of, sum of, everything added together. So all of the heats of formations of the products minus the sum of all the heats of formation of the reactants. And as I said, you can get all of that from the table. You know, and that obviously you don't have to memorize any of that. You just have to know how to read the table. So for this one, you can see how this works now. The products are the CO2 and the H2O, and the reactants are the C3H8 and the 5O2. So you can see that what we do here is it's going to be 3 times CO2, because that's the stoichiometry, 3 moles. And really, what it probably should have here is 3 moles. So we end up getting kilojoules here as the final unit. But it's really 3 moles times this many kilojoules per mole. We end up getting just kilojoules for the unit here, not kilojoules per mole, because it's kilojoules for this reaction with its stoichiometry. Technically, that's what it is. You'll notice that there's no mention of O2 over here as in the reactants, and that's because the heat of formation of O2 is 0. But all these other heats of formation were just grabbed directly off the delta H, the enthalpy table I was just showing you. Now, as far as significant figures go, this is all addition subtraction. Now, I know what you're saying. You're saying, oh, hang on. I see that you're doing a multiplication there. You're doing 3 times something, right? You're saying, you know, that's what I'm saying. I mean, 3 times something, right? So how can I say that it's all addition subtraction? Well, I'll tell you how. The 3 here is essentially a counting number. I mean, you can't have really part of a mole here in these chemical reactions. They're always balanced and they're always whole numbers. So those are counting numbers. So instead of it being 3 times negative 393.5, it's really this. It's really negative 393.5 plus negative 393.5 plus negative 393.5. So it's all addition there. So what it goes by is the number of places past the decimal. So all you need to do is look at the number of places past the decimal and take the smallest one, and that will be how many are going to be in your answer. So we've got 1 here for negative 393.5, 1 for negative 241.8, and 2 for negative 103.85. The smallest is 1, so the answer comes out to 1 place past the decimal. All right, I'm going to stop here for a second. Does anybody have any questions at all about how to do this?
So as far as significant figures go, you want to make sure the number is in the ballparks. That's why you wouldn't use the 3. You would have to use one of those. So that's why you finagled it to be like the minus, like plus minus, you just plus it 3 times basically, right?
Yes, that's right. Yeah,
Okay.
because it's a counting number. The 3 here is not subject to significant figures at all.
Oh, so it's by definition a counting number then?
Yes,
Okay.
or it has to be because of the reaction. It's exactly 3 moles of CO2.
Mm-hmm.
Exactly 4 moles of water. I mean, everything in that reaction are exact numbers of those molecules required to react.
Gotcha. All right, that makes sense.
Okay. Does anybody have any questions? Let's take a look at what you would do on the test here. By the way, if you're going to be doing those quizzes, you're going to have to use that table because my quizzes depend on those tables. Don't use tables from another book. They might have different values. All right, so this is practice test 3 on grade. I'm just going to show you kinds of problems. Oops, I didn't mean to do that. Let's try it again, preview. Here we go. Okay. So question 1 here is the kind of question you'll see on the test. Again, you can ignore the S naught. I use these same questions in Chem 2. But I consider entropy. You're just going to ignore the S naught here. We're going to focus on the heats of formation. I'm hoping you can see how you would do this. Why don't you all have a go at it now and see if you can come up with the answer. All right, so it would be 3 times 1.75 plus 19.16, and that would give you a certain value. I get 24.41. Now the thing is, don't round anything here at this point. This is a mistake some people make. They'll try and get significant figures now. Don't do that. just go ahead and continue on with the problem and do get to significant figures at the end. So I'm going to take that and I'm going to subtract, see, 3 times 21.51. And negative 75.56. And let's see, 3 times 92.66. And I get negative 242.84. So the unit there would just be, it would actually be kilojoules. It wouldn't be kilojoules per mole. And the reason is because it's kilojoules for this reaction. You might say, well, kilojoules per mole of what? Well, we don't really know. So it's just kilojoules for the entire reaction. So the unit there is just kilojoules, kJ. Does anybody have any questions about doing a problem like this on the test?
So basically, you're just taking the reactions total and subtracting it by the reactants total.
Well, products minus reactants.
Yeah, products might. Yeah.
Yeah,
Sorry.
the sum of all the, add up all the products, including the, of course, the stoichiometry, and subtract the reactants, including the stoichiometry. That's it. It's really not so bad. The math is actually pretty easy on that. Anybody got any questions? So what's that number represent? Well, it represents the change in energy going from the reactants to the products. I already know if it's negative 242.84, what that means is that that's how much energy was released going from the reactants to the products. So I know it was an exothermic process because it's negative. And that's what I can see from that. I also know that the products are a lot more stable than the reactants were. All right, any questions?
How would you write delta as a unit?
Delta?
Oh wait. What's the unit again? Sorry.
Kilojoules, kJ.
Oh,
little,
kJ. Okay.
Little k, big J.
Okay.
Yeah, you can see it up here. Little k, big J, but without the per mole because the moles got cancelled by the stoichiometry, by the moles in the reaction here.
Gotcha.
All right, any other questions? Okay. Oops. Okay, I'm going to skip over Hess's law for now. We will come back to that probably on Wednesday. But what I'm going to focus on now is the heat of reactions and bond energy. Now, I've been talking about the energy that's tied up in chemical bonds. Now, we do have a measure for that, and we can do that. We can get that measure by looking at how much energy it takes to break that bond. So, for example, well, here's a table of bond energies here. Obviously, you don't have to memorize any of these, right? You always have this table in front of you. But what I can tell you is if you've got two H's joined together, it takes 436 kilojoules per mole to break that bond. That tells you the amount of energy tied up in that bond. Now, if you look, you'll see that there are certain trends that we can look at. Look at the CC single bond versus the CC double bond versus the CC triple bond. Does anybody see any trend there? Going from CC to single to CC double to CC triple? Any thoughts about those numbers?
If you have 3 ropes attached between each other, you got to cut all 3 ropes versus like 1 rope.
Yeah, that's exactly what it's like. So you got 347, and then you got two bonds, and that's like almost double. Then you got 3 bonds, it's almost triple. So again, you know, it's the bond that gets broken, and the more bonds you have, the more energy you have to put in to break those bonds. And you can see also another trend. If you look at, say, HF, HCl, HBr, and HI, you see how the bond energies decrease as we go from HF down to HI, 565, 431, 364, 297. So we've got that steady decrease in bond energy. And the reason for that is because, you know, as your elements get bigger, like F, Cl, Br, I, if those go down the periodic table, they get bigger. It means the bonds get longer. So bigger atoms, longer bonds are weaker bonds. And that's reflected in those numbers, as you can see there. Does anybody have any questions?
So like as you go down the periodic table, it's like the distance between the two atoms shrink because they're a lot larger because they don't have that electrostatic I can't even say the word right now.
Electrostatic attraction.
Yeah.
Yeah, it's just, but longer the bond, the weaker it is.
Yeah.
Yeah.
Interesting.
So, it's easier to break it apart. Remember what breaking a bond means. It means separating two atoms, right?
Yeah.
If they're already far apart to begin with, and, they've already done some of the work for you. So these are numbers that obviously you would have in front of you. So let's look at a situation here. This is N2, and then you've got 2 molecules of hydrogen here, and we're forming hydrazine, which is N2H4. So the delta H here, you'll notice, and this is a little bit of a difference from what we had just talked about with the heats of formation. The delta H here can be, and this is an estimation here, it's an approximation. It's the sum of the bond energies of the reactants minus the sum of the bond energies of products. So it's different. Remember, for the last one, it was products minus reactants. This is reactants minus products. You might be saying, well, why is it different? Well, the reason is because when we're looking at heats of formation, we're talking about exactly that. Formation, bonds being formed. Here with bond energies, we're talking about bonds being broken. So it's the opposite. So what we do is we take all the bond energies of the reactants and we subtract all the bond energies of the products. So if you look at N2, that's an N triple bond N. You can see that that's where I get the 946 from, right, from this table down here. And the HH single bond, you can see is 436. We've got 4 NH bonds, and they're each 389. And then you've got the NN single bond, and that's 163. Now you'll notice what I've done here is I put negatives on them. And that's the reason I've done that is because when you break bonds, that costs energy. So it takes energy to break bonds. But when you form bonds, that's going to be a gain in energy. It's going to be a loss in energy. It's going to be energy being released in order to form those bonds. That's really what I want to say. So if you add up everything on the breaking side, it's 1818, and then you add up everything on the forming side, that's going to be 1719, and you subtract those two, 1818 minus 1719, that gives you the 99 kilojoules per mole. And if we were to work this out using heats of formation, it comes out to 95.4. Now you might be wondering why this method doesn't give the exact same amount. And the reason is because these bond energies here, a lot of them are average bond energies. Now, of course, for hydrogen-hydrogen, there is only one hydrogen-hydrogen bond. That's it. There's only one compound that has that. That's H2. But for a lot of others there, you've got like CHs. Where's CH? Now, for CH, there's hundreds of thousands of millions of compounds that have CH bonds. And this is just an estimate of, there you go, HC, 414. So 414 is an estimate of the energy that's in all these different bonds that have CHs in them, all these different compounds that have CHs. And there's millions and millions and millions of them. So this 414 is just an estimate, an estimated average. So that's why it comes down to that. Does anybody have any questions? All right, let me show you a couple of things. I'm going to show you a couple of things. I'm going to show you, first of all, a quiz. And I'm going to show you what this looks like on the, I'll open up another instance of my courses here. I want to show you a fun quiz here. I'm going to show you the credit quiz because it's a little bit more representative of what you need to do. Just going to show you one question from it. All right, so you can find it here. It's, okay, so it'll be bond energy. Enthalpy from bond energy quiz. So here's an example of that kind of problem. All right, so I'm hoping, what I want you to do, I don't want you to necessarily do the problem. I just want you to count the bonds on each side and what kinds of bonds. So I'll give you a couple of minutes to do that. So I want you to look at the reactant side and the product side and just figure out how many of each kind of bond there are. And if you can do that, that's half the battle. That's just math from that point. All right, so go ahead and do that, please. Okay, that should be enough time. Can anybody tell me on the reactant side what kind of bonds they got? How many of each?
On the reactant side?
Reactant side, yes.
I know I've seen HC. I got 1, 2, 3, 4, 5, 6.
Okay. I'm going to write these down as we get them. Okay, so
Oh
6
no,
by...
yeah, it's 6 on the, yeah, it was even on both
okay,
sides.
reactants. Okay, so 6 by CH. All right. Okay.
And then I got 2 CO on the reactive side.
2 COs.
Yeah.
I don't see. I don't see any COs at all.
The with the first bond, it's like the C double bond with.
No. Okay, so it's 1 C double bond O. That's what it is.
So is that equivalent to 1?
Yeah, it's 1 C double bond O. Do you see?
Oh.
Do you see over here? There's a C double bond O in your.
Okay.
Right.
I didn't realize you had to do that too. I might have screwed up a few numbers.
Well, wait, that's why we're doing this. That's why we're doing this. All right. Any other bonds on the reactant side?
We got the OH, and that's 1.
Okay, so 1 OH. That's true. All right. Anything else?
The NO, that's 1.
And single bond O. All right. Hang on. Let me take this back here. So I'm just going to put a bond in there. Okay. So 1 NO. Right. That's good. Okay. Anything else?
That was it.
I see more. I see more bonds. Anybody else? Did anybody else actually try it, or is it just Roger who tried it?
wait,
H and N.
Yeah.
Okay, how many of those, Savannah?
It was 2.
2 NHs. Okay, that's good. Any others?
CC.
Yes. How many of those, Savannah?
It was 2.
Yeah. There we go. All right. So that's all the bonds on the reactant side. I'm going to stop right here for a second. Does anybody have any questions about where any of those numbers came from? Any questions at all? So this is for heats of formation. Now this formula down here is for bond energies. And you'll notice it's the reverse. Okay. Okay, and that's for, so here's formation there. This is for bond energies. Okay, let's look on the product side. What kind of bonds do you see on the product side?
I see C double N bond.
I see double bond N. That's good. We'll go with that. Yep. Any others?
6 HC bonds.
Okay. Now remember, if you've got HC or CH, it's the same thing, Savannah. So that's fine. I mean, you can say it however you like, but just realize they're the same.
Okay.
Any other bonds?
Two C bonds.
2 CCs. Yeah. Okay.
Yeah.
That's good. All right. Any others?
1 NO.
1 NO. Yep. That's good. I like that.
And then 3 OHs.
And 3 OHs. Yes, 3 OHs is correct. All right, is everybody okay with that? Does anybody have any questions about, is anybody completely lost about what I'm doing here? Or counting those bonds, please. This isn't difficult if you know what you're doing.
Oh yeah, that's how everything works. Tell that guy that's how everything works.
I'm unmuted. I'm a little bit confused. So could you go over that last part again? I got a little bit lost in the calculation.
Just the number of bonds, David? David, just number of bonds? Because we haven't done the calculation yet. Okay.
Yeah.
Okay, so can you see my cursor, David, over here?
Yeah, I can.
Okay, good. So you got C double bond N, do you see that? That's 1 C double bond N.
Yeah, I see that.
Okay, 2 CC single bonds. I'm pointing those out here.
Okay.
That's them. We've got 6 CHs, 1, 2, 3, 4, 5, 6. That's them. We've got we've got 1 N single bond O. He's up here. And then we've got 3 OHs, 1 here for the water. So there's 2 total in the water, and then 1 up here in the product, the other product OH over here. So that's 3 OHs.
Okay.
You with me on counting those bonds?
Yeah, I'm with you.
Okay, good. All right, any other questions so far? Now we can make our lives a little bit easier here about how we do this calculation. If we look at the actual equation here, it's bond energies of reactants minus the bond energies in the products, right? So if we've got 6 CHs over here and 6 here, that means those will cancel out. I don't have to even worry about them. So anything that's not changing, I can just ignore. But look over here as well. It's like terms in algebra. I've got 1 OH over here on the reactant side, and I've got 3 on the product side. So I can cancel the 1 OH on the reactant side and turn that into a 2. So whatever the side there has more of, that's what will take on the value. I'll stop there for a second. Is everybody okay with that? Okay. We've got 1 NO and 1 NO. Those can cancel out too. And let's see, anything else? Oh, you got 2 by CCs. Those will cancel as well. Well, looking at that, now it's just going to be 1 by C double bond O, 2 by NH, and 1 by C double bond N on the product side and 2 by OH on the reactant side, sorry, on the product side as well. So all I have to do now is add up everything on the reactant side, which is going to be 1 by C double bond O, so 736, plus 2 times NH, which is same as HN, that's 389. So on the reactant side, my total comes out to be, I get 1514. Now this is kilojoules per mole, of course. I'll just say, actually, yeah, you just go kilojoules per mole. And on the product side, we've got 1 by C double bond N. Where is he? There we go, 615. Plus, and looks like 2 by OH. OH, where's OH? Okay, there we go, HO, 464. And that's 1543 for that one. Now remember, it's reactants minus products for the bond energies. So if I subtract those two, I get negative 29 kilojoules per mole. So that would be the answer there, negative 29 kilojoules per mole. All right, does anybody have any questions?
So for the sig figs off,
How would it work? Because it's 29.
Yeah, because it's because none of them have any place past the decimal. So it's all addition subtraction.
Thank you.
Yeah, in addition to that, I'd say let's make it kilojoules, just kilojoules as the unit, because again, they're moles of bonds as well. 2 times OH, for example, is 2 moles of OH essentially. So let's just make it kilojoules. All right, any other questions about that? So that gives you an idea of how we're getting that. I'm going to show you. Yeah, you're not going to like this, but I'm going to show you anyway. No, I'm in the wrong place here. Here we go. So I'm going to show you this question 2 here. Now you might be, I'm going to read it to you, and then first of all, you're going to have a bit of a conniption about it. I'm going to predict there'll be a little bit of a conniption, and then there'll be a lot of foot stamping and saying how unfair of him to put in a word problem like this. All right, but anyway, but you'll sort it out, and I'll show you something else as well. Okay, 2 seconds. Calculate the approximate enthalpy of the following reaction using the data below. 5 C atoms joined together in a straight line with as many H's connected so that each C atom has 4 bonds in total, to as many O2 atoms, which is O bonded to another, double bonded to another O, as would be required to react to give CO2, which is C double bonded to 2 O atoms, and water, which is O single bonded to 2 H atoms, and balance the reaction. And then I give you the data for the bond energies. Oh gosh, doesn't that look really nasty? Now, you might be wondering, why do I even do that? Why don't I just give you the compounds? Well, the reason is I needed this to be an accessible question, accessible to somebody with a screen reader, and putting in the compounds and then describing the compounds didn't seem to be very practical. So I decided to do it as a word problem like this, but I'll show you how this would work out. So let's just follow the directions. You know, it's like my psychiatrist told me. I told him I was afraid of stairs, and you know what he said? He said, take it 1 step at a time. So that's what I think you should do here as well. So let's look at this. It says 5 C atoms joined together in a straight line. Okay, let's do that then. 1, 2, 3, 4, 5. Oh, there we go. That's 5 atoms joined together in a straight line. Okay. And it says here, with as many hydrogens connected so that each C has 4 bonds in total. Oh, okay. So what's that mean? So that means I need 3 H's on here to give it 4 bonds. I need 2 H's on here to give it 4 bonds. H, H. See, it's not so bad, is it? If you just follow along. And then it's plus O2, which is oxygen joined together. And then that gives CO2, which is C double bonded to 2 oxygens like this, plus H2O. Now I also say that needs to be balanced. So let's look into the balancing of this. So if I add up all that together, that's going to be C5H12 plus O2 gives CO2 plus H2O. Then I have to balance this up, so that'll be 5 CO2s, let's see, 6 H2Os. 5 times 2 is 10, plus 6 is 16, so it'd be 8 O2. So that would be balanced there. So we've got 1 C5H12, and then we've got how many O's? 8 OOs. We've got how many CO2s? 5. And over here we've got 6 H2Os. So if I add up the number of bonds now, we're going to have, let's see, 1, 2, 3, 4 CCs. And we're going to have, see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 CHs. We're going to have 8 by O double bond O. Over here, we're going to have 10 by C double bond O. And here we're going to have 12 by OH. And I give you all the data down here in the question as to what you need to do, and then you can put that all together and come up with the total. So that's how you would do that. Gosh, though, it seems like an unreasonable question, though, doesn't it? Oh gosh. Can any? If only I had some other resource that would help you with that problem. Let's say you didn't come today, or you didn't watch this video. How would you know how to do it? Any thoughts?
Soft chalk, right?
Nope. No, David. No, not the soft chalk. There's no soft chalk for this.
The tutor service.
Nope. No, Roland. There's something else. Something easier than that. Is there any resource that would actually help you with how to do this problem?
Your videos on YouTube that explain each problem.
Yeah, yes, that's right, David. That's right. So let's take a look. See, it becomes a whole lot less able for people to say, "Oh, gee, that's so unfair." You know, you're stamping feet and everything else, and there's no real.
Yeah, you have your lectures, the soft chalks, and then every single question
at
the same time.
You know, this is how I teach. This is what I do. I make it so that nobody can complain. Everything I've put in my courses is due to a complaint that I've received at some point. Right, so over the years, right? And so every time somebody complains about something, I put something in the course. That's how it works. And then I've learned what I need to put in so I don't get complaints. So during the first couple of years, I got lots of complaints, right? But then, I added stuff in, and then I began to learn what people would want and anticipate their needs. So now I don't get complaints anymore. Why? Because there's nothing to complain about. So look, here's question 2A. If you've got a straight chain, this will tell you exactly how to do it. Hey, I know you can't hear this. Hang on. Hang on. Hang on.
We can
Hang
hear
on,
it
hang
through
on.
your we can hear it through your mic.
Oh, you can? Okay. All right. I'm not going to play the whole thing anyway, but I just wanted to show you. I just wanted to show you it was all explained. That's all. I just wanted to show you it was all explained in those videos. So there's actually two kinds of problems. There's straight chain and there's a cyclic one you might get as well. But again, if you didn't know how to do the cyclic one, you could always watch the video and it'll show you how to do it. It really couldn't be that much easier. Now, the thing is, you still have to put the time in, right? You know, I think that's what people, they know the resources are there, but they're thinking that they can put less time in than they have to. I think everybody, at least initially, underestimates how much time they need to put in. Yeah. I think that's been the issue, because you know you've got all the material there. You say, "Oh, look, I'll just run through it; it'll be fine." But you have to spend a lot more time on it than you think you do initially. That's the issue that I think I'm facing here with a lot of people. All right. So there you go. That's the bond energy stuff there. Does anybody have any questions? All right. Well, look, here's the thing. If you didn't do so well on test 1 or 2, then now's the time to sort of change your ways about the way you might be considering how to study for this course. So what I would do is I would make sure I practice the exam problems, the test problems that we've already been looking at. There is actually one more I didn't show you. Let me see if I can get to it. To test 3. I did mean to show you this as well. Still got a little bit of time here, so. And that's this last one here, heat and work. So what is the value of delta E? System is releasing, so you make that negative. And 11.61 kilojoules work is done by the system, so that'd be negative as well. So that'd be the delta E equals Q plus W problem. These are both negative, and that gives you your answer. So that's the kind of problem that you'll see as well. And what I would do is I would practice 1, 2, and 17. I would practice those problems on this ungraded test, and I'd start doing it now. I'd learn this as I went. See, I think what a lot of people do is they just leave it till like the day before to start studying. I don't think it's a winning proposition. I think a lot of people have lost out because they've been doing that. Yeah. So there you go. That's my advice. And also do the extra credit as well at the same time. And if you do that, then you'll be much better placed when it comes to actually taking the test. You'll do much better. That much I can promise. All right, so I'm going to leave it there. Does anybody have any other questions?
Yeah. When will this lecture be uploaded to my courses?
In the next half hour, I imagine.
Oh, great. Okay. Because I spent like the first hour of this lecture trying to fix my computer.
Oh, okay.
I just got it done.
No worries. Well, yeah, my plan was to upload it, so I will. All right, any other questions? All right, if anybody wants to hang around and ask me anything, they're certainly more than welcome to do so. Okay. All right, I'm going to stop the recording here.